Good evening. So, welcome to the third day of our physiology session. And as we'll be requiring something, just give me a minute to adjust. Okay. All right. So, good evening, everyone. And let's start with our today's topic. All right. Now, see, as we talked about, that we'll be starting with that point where we left off yesterday, right? So, our today's topic would be we'll talk about oxytocin and prolactin, then ADH and thyroid hormones. So that's what is in our platter today. We'll complete at least this much because then today we are on the third day. We do have fourth and fifth day with us. So that's where we'll be covering that pancreas, ACTH, gonadotropin hormones, and the sixth day, that is obviously our the test day, right? So before that, I would like to cover as much as possible. Okay, so let's start with our today's session, right? As we said that oxytocin, right? Oxytocin and say prolactin. They both are of extreme importance. Right? Yes, good evening. Now let's focus on the subject. Okay. Yeah. So yes, very warm. Thank you. Okay. So oxytocin, say where it is important. Oxytocin will be acting at two places, right? Two places. One, it will be acting on the smooth muscles. We'll be seeing it in more detail, but say for the glandular secretion, that is for the secretion, it will be acting on smooth muscles, right? It will be acting on smooth muscles. And second, for the uterine contraction, it will be playing a major role because that uterine contraction, which will be an important stage in parturition, right? That is delivery of baby. So delivery of baby, that is where it will play a major role. Prolactin, as the name suggests, lactin, that is for milk production. Right? So we'll see that how the entire thing is orchestrated right from the pregnancy till the breastfeeding, that how these hormones they work with each other. Okay. Before that, just a very high speed thing, that is, sorry. So that is in case of hypothalamus, which will be acting on to anterior pituitary A. I'm for pituitary, I'm just writing P. A is for adeno means it is glandular, right? So that would be secreting. Say in our case, that is for today, there were lactotrophs. You remember that? Lactotrophs, right? Lactotrophs. So we picked it up from that fat, right? This was FSH, this was ACTH, and this was thyroid, right? So over here, these were what? These were basophilic, correct? These were basophilic. Apart from that, whatever was left out was all acidophilic, right? In acidophilic, we had growth hormone and we had this lactotrophs, right? So that is where the prolactin was getting released. So this is the lactotroph which would be releasing prolactin, right? Growth hormone is somatotrophs, right? Somatotropin. Now, by mistake, yesterday someone pointed it out, and really thanks to her, because at one point, say I corrected that thing in PDF also. So instead of somatotropin, by mistake it was somatostatin was written, but just below it was correct. It was somatotropin, but I corrected it, right? So now it is, in case if you have downloaded that PDF file yesterday, download it today, right? So that it is corrected. So that was in at one place it was by mistake. It was somatostatin was written. Tomorrow we'll be discussing the pancreas. So that's where we'll be talking about in detail about somatostatin, right? Okay. So this is like lactotrophs, right? They will be releasing prolactin, and lactotrophs, they are acidophilic. Acidophilic, that means they'll be straining the red, right? Red or dark. And basophilic like blue, right? And as we were talking about that for males, blue, purple, they all are same color, right? So that's how we remember that basophilic is blue or purple. Regarding the posterior, posterior is like neuro. Neuro means it is in continuation. That means all these hormones, they will be released in, will be prepared by hypothalamus only. So that means we are talking about oxytocin. Oxytocin, it is produced by hypothalamus, and it will tell that okay, posterior pituitary, you just store it, right? So it is stored there, right? It is stored here, and when it is stored here, so it is called as herring body. Herring body is what? Herring body is just that dilated, it is dilated axon, right? Excellent. PDF, there is in the comment, in the description of every video, there is a complete link, right? There is a complete link, and when you go to that, all the PDFs are available. In case if you have got still a problem, in case if you are not getting, send a mail, right? I'll send you the link. Okay, because it is necessary, exam is coming right on Saturday, so you need to go for, yeah, it is in description, it is there. But in case if you don't get it, don't hesitate in sending a mail, because on the exam day, no excuse, right? So do get the PDF, confirm it that you get it properly. Okay, all right. So this is in brief about those dilated axon. It is necessary over here to remember the name. It is necessary to remember the names of those say nuclei, because I'll be asking it in exam, right? So they are like paraventricular, right? Paraventricular and supraoptic, right? These are, on the first day I said that you just have to remember these two important nuclei, because they are like the direct extension all the way coming from hypothalamus, coming down to posterior pituitary, and in the dilated axons, that's where these oxytocin is stored. One more, ADH will also be there, right? And that also will be discussing separately, but right now that's our focus. Okay, all right. Now this prolactin, right? This prolactin in normal case, right? This prolactin, it is inhibited, right? Because its importance is only during certain stage of life. So for rest of the life, that is apart from pregnancy, for rest of the life, prolactin is inhibited, right? Plus in case of males, in men, that is inhibited, because if there is any such abnormal secretion, that is what will lead to so many complications. True. While this oxytocin, that is also this oxytocin, because it is normally not needed, right? Normally it is not secreted. It is only during breastfeeding, that is during the nursing time, that's where the oxytocin has got importance. But But there is one important thing. That's what we talked about even on first day also. Oxytocin is something which is quite important for females, especially whenever, say, during those intimate moments when female is at its her peak, right? That is where there is some release of oxytocin, right? So that's what is called as the orgasm, and that is what leads to what's called as the afterglow on her face, right? That is what is called as the afterglow. So that's the reason that in normal life, say, oxytocin is released in some amount, though this amount is very less, but its importance is pretty high, right? From psychological point of view, it is pretty high. Okay, so for rest of the life regarding the prolactin, right, this is all restricted. Now, how it really happens? Say, what hypothalamus does is, hypothalamus knows that these hormones, they are not needed under normal circumstances, right? So it releases one, what is called as the dopamine. Dopamine is prolactin prolactin inhibiting factor. And this keeps on firing so that prolactin is never released, right? Only during that pregnancy and only during certain states, that's where it will work. Now, as we just saw that this prolactin, they are released by lactotrophs, right? So obviously they will inhibit lactotrophs. So when the lactotrophs are inhibited, obviously it will not lead to any secretion. And yes, we are talking about anterior pituitary, correct? We are talking about, time to time I'm telling you because I'll be asking questions on this also, right? So this is anterior pituitary. Remember, this is, we are dealing with anterior pituitary. Posterior is dealing with only something which is in direct continuation, right? And that is like, say, oxytocin and the ADH, anti-diuretic hormone. Okay. Dilated axon means normally the axon is like this, right? But then there are certain areas which are dilated. They are like dilated, and it is in this dilated area where these neurotransmitters, they are stored, right? And then they are ready to release. So these are called as the herring body, right? These are called as the herring body. In case of any doubt, just go through that first, our day one, right? Still this much is there. It is called as herring, HERRING, herring bodies, right? Okay. Well, regarding one question, see, the orgasm is, that is then when the male and female meet, that is at the height of the pleasure. That is what is called as the orgasm, right? That is what is called as the peak of that pleasure. It itself is a huge topic, and yes, definitely we'll be touching that topic when we'll be talking about, say, it in psychiatry, right? Okay. Now, say, oxytocin, we now from this point onwards will take the oxytocin and prolactin together, right? Because we really wish that to see the entire process, how it really works. Say this, both these hormones, they work on breast, right? Now it has got 15 to 20, about, say, lobules, right? And then in every lobule there is alveoli, right? Now these alveoli, they are lined by simple epithelium, right? So if we really draw it like this, right, they are like this, right? So over here it is lined by simple epithelium. So simple epithelium is just one layer of epithelium, right? There are cells. So Simple means it is one layer. Simple squamous epithelium. Now over here, right, the simple epithelium. Now over here, these are the milk secreting cells. They are milk secreting cells. And then that milk is accumulated at one point, and from here it goes into what is called as the lactiferous ducts, right? Lactiferous ducts. To see this bit with more clarity, the important point that if we really draw it, right? So that's the pectoralis major, and over here these are all the say lobules, right? And they open into the form of lactiferous ducts, and they open into the nipple. Now, if I just zoom this part, right? Zoom this part. So these ducts, they are having muscles. They are having muscles. That is what is called as the myoepithelium, right? That is the myoepithelium. Now, this myoepithelium would be affected by those hormones, right? So we are learning this because at every point these hormones will be coming into picture. Okay, so how much have we learned? We talked about 1 point. We talked about 1 point. I'm answering of third part of it. Okay, okay. So one, what we talked about, that is milk secreting cells, that is 1 point. Second, myoepithelium, right? That would be the most important point. Okay, so it happens in this way that, say, in the nipples there are oxytocin. It is oxytocin, right? Not prolactin, only oxytocin. Okay, so there are, say, tactile receptors, right? These are the tactile receptors. Tactile means they are affected by suckling of the baby, right? So when the baby suckles, suckling of the baby. So when the baby suckles, so at that point, it leads to release of oxytocin. And this oxytocin, right, will be affecting myoepithelium. So there will be contraction of myoepithelium, right? And that leads to, say, helps in milk release, right? So there would be several such mechanisms. So now we are learning this first mechanism, right? And that is how these tactile receptors, they work. Got it? Okay. Now next is, so during pregnancy, what happens? During pregnancy, all these hormones, they are working, right? Not only, say, oxytocin, there is prolactin, because body knows that it is necessary to prepare the breast for the milk production. But parallelly, there are estrogen, there are progesterone, right? They are also there. From where does estrogen and progesterone are coming? They will be coming, they will be produced by placenta, correct? They will be produced by placenta. So all these four hormones, they are working together. Now they will be acting on the growth of alveoli, right? It is the prolactin which will be working for the preparation or the production of milk, right? So because the alveoli, they are growing, so that leads to increase in size of the breast, right? Increase in the size of breast. But this breast is not producing any milk. The reason that estrogen and progesterone, they know that milk will be required after the birth of the baby, right? So right now it is necessary to inhibit it. So here milk production, say, is inhibited, right? It is inhibited. These are the questions, right? Right now we are not touching, right? Because Abrar, these are the questions which will completely distract from the main topic. So that's why we'll not be touching those topics. You can send a mail. Okay. So oxytocin, prolactin, estrogen and progesterone. Estrogen, progesterone, they will inhibit the secretion of the milk, right? Because it is not needed. Now, but as soon as the baby is born, what really happens is that, say, during labor, right? That is for the delivery. How it is said that it is initiated? That is dilatation of cervix, right? As soon as there is dilatation of cervix. So here is like, say, uterus, right? That's where the baby is, right? That's the placenta, umbilical cord, right? That's the nose, right? And as soon as the cervix is dilated, right, it is said that, okay, the labor has initiated, it has started. Now, when the cervix is dilated, this is dilated cervix. This dilated cervix would send a message to the hypothalamus, right? It will send a message to hypothalamus. And in response, hypothalamus would increase oxytocin, right? It will release oxytocin. This oxytocin, it has got effect on cervix. It has got effect on even the uterus, right? But right now, let's focus on cervix. So because of increased oxytocin, there would be more dilatation, right? So cervix is more dilated. This is what is called as the positive feedback. Positive feedback. Now, as cervix would be more dilated, again it will be send the message to hypothalamus. Again, there will be still more increase in the oxytocin, and there will be more dilatation. So this process will keep on continuing. When this process is continuing, right, so it leads to, it is affected or it is supported by one more thing, and that is this increased oxytocin will affect uterus, right? It will affect uterus. It will lead to uterine contraction. So now the uterus is contracting. So these both processes, they lead to delivery, successful delivery of the baby, right? So that's what leads to uterine. So we'll write over here uterine contraction, right? Uterine contraction. So two things happened. One was this cervix dilatation, and second was uterine contraction. These are two effects of increased oxytocin, and that is because of positive feedback mechanism, which was initiated by the dilatation of cervix, and that dilatation is because of the pressure of the head of the baby, right? Dilatation means, say, increase in the curvature, right? So normally it happens like this is uterus, right? So it is cervix is closed, right? Cervix is closed. But when the baby's head comes over here, so this expands, right? So dilatation or expansion, you can also say expansion, right? That is what is called as dilatation. Okay. Yeah, that's right. Increase in the space. Right. Gentlemen, vasopressin right now we are not discussing. It will come. I'll let you know, because vasopressin is anti-diuretic hormone. It is completely a different thing. So please focus on the subject. Okay. Right. So that's what really happens. So that's what really happens in case of labor. Now the baby is born, right? So baby is born. First thing what really happens is that placenta is gone, right? If the placenta is gone, immediately there would be decrease in estrogen and progesterone, right? These two level, they are immediately decreased. I'm turning the chat off for some time, right? I'm turning the chat off for some time, not because say some of the questions which are I'm again and again telling, why are we discussing the kidney, or why, Cherry, even you are answering that when we are dealing with something different. As I'm telling that ADH will come and we'll be talking about it, right? So unnecessary, why to deviate from the topic? Say it's like for 10 weeks we are together. Even after that, right, when we are supposed to learn, so we need to keep some discipline. This is something which is really not good, right? So that's why I'm turning the chat off, right? I'll turn it off at a later stage, right? I'm right now turning it off. Okay. Though I don't like it that way, but still there is no option. Okay. So let's focus. This is like baby is born, placenta is gone, there is decrease in estrogen and progesterone. The moment estrogen, progesterone are decreased, immediately prolactin will come into picture, because it was estrogen, progesterone which were preventing those milk secreting epithelial cells, right? But now they are decreased. So prolactin is now in action, right? So this prolactin will act on milk secreting epithelial cells, right? So milk would be produced, right? And this milk, right, that is when the baby would be feeding, that is when there is breastfeeding, even that would also lead to increased secretion of prolactin. So once again, what we are watching is the positive feedback mechanism, right? So this becomes like a cycle. So that's the reason that milk secretion, it leads to breastfeeding, and that breastfeeding is leading to increase in prolactin secretion, and it goes on and on. So that's like two things. Say prolactin increased and oxytocin. Oxytocin was acting on those myoepithelium, right? So when those myoepithelium, they were contracting, that means it was leading to push of the milk, and prolactin was handling that epithelial cells. So prolactin was handling the milk production, and the oxytocin was taking part in the expulsion of the milk. Okay, there is one more thing, that is in case of prolactin, right? In case of prolactin, when the prolactin is increased, it will be inhibiting gonadotrophic releasing hormone, GnRH. Now because of that, what happens? Gonadotrophic releasing hormone, it affects luteinizing hormone and follicle stimulating hormone, right? So they are also decreased. When they are decreased, luteinizing hormone and follicle stimulating hormone, they both are vital component for a normal menstrual cycle, right? So they are needed for the process of ovulation. So what a menstrual cycle is, it is nothing but every month one ovum is released. It travels all the way, right, in the hope of that yes, it would be fertilized, and then the uterus is prepared. Then if there is no fertilization, then entire lining of the uterus which has been prepared, it is shedded, it is broken, and because it was loaded with blood, so that is what is released. Now over here, because luteinizing hormone and follicle stimulating hormone, they are also suppressed. That's the reason, therefore, right, it is seen that females, right, they don't ovulate, or their cycles, right, menstrual cycles, they are not there during breastfeeding, right? During the breastfeeding or during their nursing time, right? It is because of the inhibition of luteinizing hormone and follicle stimulating hormone. So that's how, say, these important hormones, they play the major role, right? Moving on quickly to ADH, anti-diuretic hormone. Now, say I really don't like turning the chat off. Really. I feel that it's okay, everyone should be allowed. But when things go beyond, means beyond a limit, and not only that, in spite of repeated request, when unnecessary questions, which we know even by a common sense that they are not at all related to the subject, that is something which I don't like. I even if you write just one sentence and that please explain this topic again, I don't mind explaining it 10 times, but it has to be on the target, it has to be specific, right? So it doesn't matter, right? So as we have to do learn so much today, so I'm keeping the chat off only. Okay. So ADH, anti diuretic hormone. Diuresis is, right? Diuresis was what? Diuresis was when it is said, let the water go, right? Let the water go. So it goes into the form of urine. So anything which is, when we say diuresis, so that means it is allowing the water to go. It means it is increasing the urine output. It means it is decreasing the blood volume, right? It means it will be decreasing the blood pressure, right? Got the idea? Again, right? When the amount of water is increased, that is when the urine output is increased. That means from where this urine would be prepared? Obviously from the body fluids, right? So when that fluid is decreased in the body, fluid would be decreased in the body, right? So that is what is called as the blood volume. So when the blood volume is decreased, right, blood volume is decreased, so it would decrease the blood pressure. So that's the reason that in pharmacology we'll see that so many drugs which will be acting by the principle of diuretics, they are used as antihypertensive, right? Like a Lasix, right? So that is what is used as the diuresis. Yes, in pharmacology we'll be touching these points, right? Okay, one more important thing, the ADH, the another name of ADH is vasopressin. Vaso, I'm breaking this word, otherwise it's a single word, but I'm breaking it for a purpose. Vasopressin, right? This is one single word. Vaso means, you know it very well, it is vessels, correct? Pressin means pressing it, it means contracting it, so it would contract, right? So it is the contraction of vessels. Now when the vessels are contracted, right, so again it is the same thing, it is decreasing the it is like when the vessels they are contracted, so they'll be increasing the blood pressure, correct? They'll be increasing the blood pressure, because over here what we discussed was diuretic component, while this ADH is just the reverse of its anti-diuretic. So over here anti-diuretic, right? So I'll just draw it like this diuretic portion which was described over here, and we are supposed to discuss anti. So anti will do everything ulta, so it will resorb the water back, right? So over here the water would be reabsorbed, so we are not letting absorbed, so we are not letting the water go. So if the water is not allowed to go, obviously it will increase the blood volume, right? And once the blood volume is increased, so it will increase the blood pressure. on top of it, as we said, so this is one action. The second action is this: it will constrict the vessels. So when the vessels are constricted, right, again, the area was this much, the fluid remains the same, but now the vessels are constricted, so automatically the amount of pressure generated on every wall is increased. So that is what is called as the blood pressure. Pressure generated by blood on the walls, it would increase, because previously it was this much, now it is this much. So obviously same amount of blood volume, it will increase the pressure. So that's what really happens, and that is what is called as the ADH, right? Anti-diuretic hormone. Where is it produced? Definitely, you are right, that is produced in hypothalamus. Very good, right? Because this is something which will be synthesized, which will be produced in hypothalamus and stored in posterior pituitary. That's right, because A was anterior, anterior was adeno, they were secreting those hormones by itself. This is not secreting, posterior is just storing. When the posterior is storing, right, I said that you need to remember two nuclei, one which was near to the ventricles, so it is paraventricular, right, paraventricular, and second is supraoptic, right. These are the nucleus which will be say releasing this, right, and their extensions, they are in the form of axons, and that's where they will be stored. Now this ADH, is released into the bloodstream, right? It will be released into bloodstream. How come? Say this ADH, that would be stored into the posterior pituitary, right? In those herring body, right? In those herring body, and these herring bodies, they will be releasing it directly into the bloodstream, right? So when it occurs like this, there has to be, because ADH will immediately start acting, right? Now, before we really proceed, just, I know you must be knowing about this, but still I am explaining it so that I don't want to keep anything in doubt. You know the osmolarity, right? What is osmolarity? Let's say this is a vessel in which there is water, right? There is water. We add some salt into it, right? We add some salt into it. So we'll call this salt as solute, correct? We'll just name it as solute, something which we are mixing in it. And let's say this is 2 liters, right? 2 liters. Now, what if somehow, right, we take out only the water out of it. We keep the salt as it is, whatever the amount of salt we have added, right? 3-4 spoons, whatever. But we take out the water. So when we take out, now it is 1 liter, right? So in 1 liter of water, the amount of solute salt, let's say it is 10 grams, right? Just for example. So here also it is 10 grams of that salt, right? But the water is less. So this means that the actual concentration of salt will be higher in this 1 liter, correct? Right? That is what is called as the osmolarity. That is how much solute in proportion is mixed. It is the proportion. If it's like I cut down this thing to 5, so then the osmolarity, technically it is called as the same. This is just 2 liters, this is just 1 liter. So that's how things go, right? It is based on the concentration. It is not based on how much it is, but it is based on concentration, that is concentration of both the components. That is how much solute is there, how much water is there, and that's what is called as the osmolarity. Now we are talking about it, say in case of dehydration, right? What happens in case of dehydration? There is severe water loss, right? So there is water loss, but proportionately the salt loss is not that high, right? So salt loss is, there is salt loss, but proportionately less, right? Proportionately, it is less. So it means in this situation, water is lost more, solutes they are relatively less lost. So this leads to increased plasma osmolarity, right? Increase plasma osmolarity, right? So its concentration increase. Now there is a very fine quality control system into our body, because it keeps on checking every second that what exactly is the concentration, what is the osmolarity, because this osmolarity has got so many side effects, so many effects. I'll not say side effects, so many effects. Say it is said that you take one almond, right? You put it into water. Next morning, when you see the, yes, it is swollen so nicely, right? That almond, you put anything, right? It is swollen. It's because the concentration, those solutes, they were very high into the almond and there was less water. Surrounding there was so much of water. So that water entered into that almond, so that that concentration is same. Concentration of that solute is made same. Water always tries to travel to make the concentration same, right? So that's what really happens. So this is like, say, that almond, right? And there is so much of water. Outside there is less of the salts, inside there are more. So water would travel like this, and that would lead to swelling of the, right? It would be expanded, it will bulge, right? That's what really happens. Okay, now when we learn medicine, there will be so many things associated. All those fluids which are given, right? Ringer lactate, or say normal saline, or say instead of say 0.9% NaCl sodium chloride, right? Which is also called as the normal saline. There are even other concentrations available in the form of half concentration, double concentration. So what exactly, in which condition should we go for it? That would be what we'll be touching in medicine. Yes, in medicine we'll be dealing, I was writing the topics, we'll be dealing with these, that which fluid to be given in which situation and the reason behind it, right? Okay, so what's that quality control, right? What is that quality control into our body? Now, as we said, that anti-diuretic hormone, right, ADH, what it is doing, it is just telling that let's not lose the water. Simple. So absorb the water back. Tell the kidneys that don't let this water go, absorb it back, so that we maintain our blood volume, right? But what happens in normal case, right? Nothing has happened, body is running normally. So this is the quality control. This quality control, which is a super control. So if it's a super control, super means it is a very good control, super control, right? So from this super, we remember the word supra, right? Supra, right? Or you can say even super also in style, you can say supra, right? So good. And this supra is nothing but it is optic. So supra optic nucleus is our super control. Now this is what, why? Because in this there are osmoreceptors. Osmoreceptors. We are writing receptors as R and circle, right? So it is osmoreceptor. This osmoreceptor is doing what? Simply name itself is suggesting that it will keep on checking the osmolarity constantly. So this is like a constant check. Constant check, right? How is it doing, right? Say in this case, let's say this is one of the cell of this supraoptic nucleus. Now in that case, there are channels, right? They are called as the name. See how creative the name is. Aquaporine, right? Aqua is water, and water is poured from here to here and here to here, right? So water can go from here to here and here to here. Because such aquaporine channels, there are so many. So let's give some specific name for this and that number is say 4, right? That number is 4. Where are 1, 2, 3? Yes, it would come, right? So please wait. So this is our one cell of supraoptic nucleus, which is responsible for this constant check. What it really does, it has got osmoreceptors, right? It has got osmoreceptors. Now over here, this cell has got this aquaporin 4. So whenever there is increased in concentration, right? So let's say there is increased osmolarity, so in this case, increased osmolarity means what? There would be more number of those solutes over here, right, as compared to here, right? Immediately it will say, okay, water from the cell go out and neutralize these guys, right? So this water, it will say go out and neutralize, that is maintained, right? So this is where the water would start traveling. So what would happen? The result would be there would be shrinkage. There would be shrinkage of this cell, right? This cell would shrink because water has been extracted out due to this osmolarity principle, right? It will extract it. So this would shrink. This would shrink. And when it would shrink, it would send a message to hypothalamus, right? When it would shrink, it will send a message to hypothalamus and will tell this guy to drink the water, right? Because osmolarity has increased and I am losing the water to neutralize that solute. So, and that's what is called as the thirst response, right? That's what is called as the thirst response. But at the same time, hypothalamus would tell that I need to inform kidneys, because kidneys, so they'll keep on throwing the water, and here we are thirsty, there is so much of less water, so release ADH. So ADH is like a messenger. ADH will say that, boss, don't worry, I'll go to kidneys and I'll tell them not to waste the water. Whatever the water which is going out, absorb them back. So it will go to kidneys and will say, do this. Kidneys will say, okay, no problems. This is like, say, Bowman's capsule. This is proximal convoluted tubule, right? Then there is loop of Henle, and then there is proximal and distal convoluted tubule, which will open into that collecting duct, right? So it will say that, well, this is the area, this is the area. These are the areas which would be targeted, right? Proximal, sorry, this is, yeah, right? So it will say here and here. Proximal convoluted tubule and the distal and the collecting duct, right? Collecting duct. Yeah, that's fine. So proximal convoluted tubule and the collecting duct, that's where it would act and it will take the water back, right? So that's where the resorption would occur. So this is first point. This is the first point. Now, how actually it would really do it, right? There is what is called as the vasopressin receptor 2, right? There is, so over here in case of this PCT and collecting duct, right? There is vasopressin receptor 2. This vasopressin is G protein coupled receptor, right? So it is like that 7 pass. So what it will do is it will convert ATP into cyclic AMP. This is the important step. It will, because say there has to be some mechanism, na? Right? So that ADH comes, anti-diuretic hormone comes, ADH or vasopressin, right? It is the same thing, right? ADH or vasopressin. But name of the receptor is vasopressin receptor 2, right? Vasopressin receptor 2. So this vasopressin receptor 2 will act so that cyclic AMP is released. And this cyclic AMP will act on, again, aquaporine. But because now the site is different, so that's why we are giving it another number, aquaporine 2. So it opens up these channels, right? So when there is increase in aquaporine 2, right, it means they will be acting here. They will be acting here. So these channels would open up. This channel will allow water, right? They will allow water. So that water would be allowed to come out. Come out. Now from where would they go? Okay, over here there are all the capillaries, right? Blood is there. So they will enter into the blood. Simple as that. They will enter into the blood. Right? So it means these aquaporine 2, they will actually allow water, right, to be extracted from urine to the blood, right? So over here the water would travel, right? Water would travel towards and into the blood. So thus blood volume will increase, blood pressure will increase, and that's the effect of ADH. And not only that, vasopressin is going to constrict all those vessels, right? So that's why it will be increasing the blood pressure. Correct? So this is what really happens during this entire process. Now let's say when the person starts drinking water, right? So say here is the person, right? He drinks water. So you can guess it now very clearly what would happen. So when the water, it is just the reverse of this entire thing. So because of this, right, ADH should be affected. Yes, it would be affected because actually in hypothalamus, what was that name of that nucleus, that supranucleus? That is supraoptic nucleus, right, which is constantly checking. Because of increased water, osmolarity would drop. True, right? Because now you are drinking plain water. So amount of solutes, they are fixed. More water has entered, so now it is diluted. So that is decrease in osmolarity. Decrease in osmolarity. So this supraoptic nucleus, that is sitting for that purpose only. Supraoptic nucleus, right? Immediately it will say, okay, I don't need to send the water out, right? So it is all good. There is no constriction. If there is no constriction, that means it would not send the signals to hypothalamus, right? Hypothalamus would not release ADH, right? It will not release that thirst response because things are good. If ADH is not there, then it won't be acting on the principal cells of that proximal convoluted tubule and the collecting duct of the kidneys. So if that is not affected, then those aquaporine 2 channels, they will not be opened. If they are not opened, in that case, water will not be reabsorbed. So water reabsorption will not be there. So there would be increased urine output. That's right. So that's how things go. This is very intricate balance. So it keeps on balancing in such a way that the amount of blood volume in any of the condition, it remains almost the same, right? That's what, because it is governing the blood pressure also. Every system is affected when there are some changes, right? Changes in the form of, say, some emergency. Let's say if there is hemorrhage, right? Let's say if there is hemorrhage, rapid and lots of blood is lost. So let's make it a massive hemorrhage. Or if there are burns, because in burns there is severe loss of body fluid, right? So let's say it is third degree burn, right? Deep burns, and in which case there is severe loss, right? Severe loss of body fluids or the plasma fluids, right? Severe loss. When the blood plasma is lost, it will actually lead to sharp decrease in the blood pressure, right? Blood pressure is decreased. So that's the reason that in such cases, your entire say attention or the focus should be to take care of this blood pressure. Now see what happens when the blood pressure is dropped, right? When there is low blood pressure, there is one more mechanism. Now, they were, what was that receptor which was into supra-optic nucleus? It was osmoreceptor, right? Which was checking the osmolarity. That is how much salt you have got, how much salt I have got, right? So let's check that sample. If the percentage is same, that is in your case also it is 5% salt. I am also having 5% salt. All right. No movement of the water. But if I have got 10% of salt and on your side if it is 5%, so then what would happen? Salt is more over here. So then water from your side will start traveling towards my side so that it is neutralized. They both should be having the same concentration. That was osmolarity. Over here we are dealing with pressure. So that's why they are called as the baroreceptor. Baroreceptor. Baroreceptors, they are also called as pressure receptor. Correct? Pressure receptor. So their function is they constantly keep on checking that is the pressure okay, is the pressure okay, and they understand by this thing by that how much is the stretch, right? Because if there is more pressure, so they'll stretch and immediately they'll run to the higher centers that or blood pressure is increasing, right? Do something. So where are these pressure receptors? That's what this is, arch of aorta, right? From arch of aorta, there would be major vessels which will be coming out. But one important thing that when we touch over here, right, this is carotid, right, whose pulse you can very well. This is external carotid. Now, say carotid artery and arch of aorta. These are the areas. These are the locations where there are baroreceptor pressures. Right? Now, if there is low blood pressure, so they will send the message to hypothalamus. Right? They will send the message to hypothalamus. What message they would say? They would say blood pressure is less. Blood pressure is less. That means we need to preserve water. We can't let the water go out. Right? So hypothalamus, what you do is you create anti-diuretic hormone, right? And in large quantity and send it into the blood so that kidneys will stop throwing that water out, right? So that kidney will go into the process of anti-diuresis, ulta, right? So that water is not lost. Fair enough, right? So far, things are good. But then there is one more thing. As we said that these are the baroreceptors, fine, they worked good. So we'll mark this thing as 1. Right? Story is not yet complete. This low blood pressure will also go at one more location. Right? And that location is where there are thousands and thousands of small receptors are there, right? These are carotid and arch of aorta, they are like big boss. But then there are some chota centers. Those centers are, let's say this is Bowman's capsule, right? And then there are convoluted tubules. But in Bowman's capsule, right, there is afferent and there are efferent vessels, right? And then there are all, this is what is called as the capillary tuft, right? It is what is called as the capillary tuft, tuft. It is there, right? All good. Afferent and this is efferent. Afferent is coming and efferent is exiting, right? Always remember it like that, right? In Hindi, it becomes much easier. Afferent is aati hai, right? Efferent is exiting. And in brain also, it is with respect to that. Nerves which are coming, they are afferent. Nerves which are going, they are efferent. Right? Okay. So this is capillary tuft. Now just near the afferent, there are these cells. These are JG cells. Juxta glomerular cells. And these cells, they are nothing but they are the receptors, right? They are the receptors. They are like baroreceptors. They also sense the pressure. Now, when they sense the pressure, they will release an enzyme, a very important enzyme, right? Which is called as the renin. That's why whenever you deal with kidney, there is one mechanism which is called as the renin-angiotensin system. And once you have understood this, the pharmacology becomes absolutely easy. Because then, when you will understand this renin-angiotensin system, you have understood two things clearly. One, that blood pressure can be managed by increase or decrease of the blood volume, right? And for that we can talk to ADH, that let the blood, don't let the water go, and then we manage. Second, those baroreceptors, right, which are into carotid artery and arch of aorta. What if we really want to raise the blood pressure, right? We want to raise the blood pressure. So in that case, when we want to raise the blood pressure, any of the stimulation to these baroreceptors, right? Because they will be telling what blood pressure is decreasing, right? So that will message would be sent to those hypothalamus and increase the ADH and the whole process. So there can be few drugs which will be acting on that part. But this which we are about to talk is renin-angiotensin system. More the steps, at more points you can really work on. Got it? It's like a Formula car race. If there are more pit stops, so at every pit stop, yes, you get the facilities, right? Or in Formula car race, so you don't need so many pit stops. Let's say it is a marathon run, right? So whenever there are these water centers, rehydration centers, right? All those nourishment centers, so you can have so much at those points. Similarly, in renin-angiotensin system, there are so many stations. There are so many things which are happening. So whenever things are happening, right, you can have any of the medicine which will be acting on specific location, that is specific process. Let's see it to make it still easy. So this renin is released, right? Renin is released. Why? Because from the juxtaglomerular cells. Juxtaglomerular cells, they are near this afferent vessels, right? They are near afferent vessels. Okay. So this is renin. This renin, now liver comes into picture. Yeah. Right? Liver tells that whether you call me or not, right? I am like a very sincere person. So this liver will keep on producing one hormone, and that is angiotensinogen. Tensinogen. Right? It will say, I'll keep on producing it. And I'll keep on throwing it in blood. So that the moment that renin comes, renin should not be in trouble, right? Renin should get this angiotensinogen immediately. So they really both make a couple, right? So with this, it is always in blood. But because now the blood pressure has decreased, that renin is released. When renin is released, so both of them they meet, and then there is release of a new substance, and that is what is called as the angiotensinogen or angiotensin, 1, angiotensin 1 is released. This angiotensin 1, see how many organs they are involved, right? This will reach to the capillaries because it is, again, it is into the blood, right? This entire game right now, it is in blood, right? So obviously they will divide, and finally they'll reach to the capillary, and that also lung capillaries, right? So all those capillaries of lungs, right, they are now into action, so it reaches to those lungs. Now in lungs, this leads to one more secretion, and what it is, these lungs, they would say that, see, we do have one special enzyme, and that is what is called as the ACE, right? You have got the best enzyme, ACE enzyme, right? It is angio, see, name itself is easy, angiotensin converting enzyme, right? It would be converting something, so it is angiotensin converting enzyme. What it will convert? It will say that, see, angiotensin 1 is a very tough language, right? That bichara hypothalamus won't understand. So this angiotensin 1, let's convert it into angiotensin 2, and that is by this enzyme, angiotensin converting enzyme. He does this. Now this 2, it can be sent to talk with hypothalamus, right? So now it is easy, right? But see how many organs they got involved. All the way from this low blood pressure, it led to juxtaglomerular cells. Juxtaglomerular cells, they produced this renin, right? This renin, it met angiotensin, which came from the liver, and it led to formation of angiotensin 1. This angiotensin 1, because it is in blood, so it reaches to the lung. In lung, there is another enzyme sitting, right? It will say, see boss, this is angiotensin 1, no one would understand. You need to get converted to angiotensin 2, done, and then that would go to the hypothalamus. And then hypothalamus is said, we say to hypothalamus that what would you do, right? What would you do? He'll say you increase that ADH, right? Increase ADH, increase anti-diuretic hormone, so that it will go to kidneys, and then it would say that yes, let's save the water, don't let the water go, correct? So that's how this ADH would actually work. So one, it will increase that aquaporine, right? It will increase that aquaporine 2 in numbers, right? So that more water is taken back, right? So it is what is called as the water resorption. So more water is taken back, and that's how the fluid is balanced, right? At the same time, as we said, that it will be acting on smooth muscles of vessels. So ADH will lead to contraction. It will contract these vessels, right? That means there would be increased vascular resistance, right? Vascular resistance is increased. What is that? So all those vessels, they were like this. Now they are compressed, right? So now blood cannot flow through it easily. So this would lead to increase in blood pressure, right? And that increase in blood pressure, it means pressure is increased. Pressure is increased, so it will go to where? All those baroreceptors, right? Pressure is increased, so it will say, okay, the pressure is increased, so hypothalamus, now you can say cut down the ADH. Done, right? So that's how the system is managed, right? That is how the ADH will take care of it. So this was about our, I'm saving this file and it is saved. So this was the second topic of today. Now we move on to the third topic, and this is absolutely marvelous topic, thyroid, right? How intricately everything moves, right? That's what thyroid will be doing, right? Very interesting. Okay, turning the chat on. If everything is fine, then I'll keep it on, else we'll again turn it off, right? Because in benefit of everyone. Okay, so let's say in case of thyroid, what really happens in thyroid? Same thing. Here is the hypothalamus, right? Hypothalamus. This hypothalamus will be talking to pituitary. We are not writing anterior or posterior, right? So we are not talking about anterior posterior. We decide what was it doing. This is thyroid, right? Thyroid. So it is T. T was what? That we remember that fat, right? Follicle stimulating hormone ACTH and thyroid releasing hormone, right? Thyrotropic releasing hormone. So this means that this is what we are dealing is basophilic, right? So this is for the basophilic, right? So here is thyrotropin releasing hormone, that is from hypothalamus, and pituitary that would release, and this would be which pituitary? It would be the anterior pituitary, correct? Because it is adeno, right? And it will lead to thyroid stimulating hormone. This thyroid stimulating hormone would really go to thyroid, right? It will really go to this thyroid. And from thyroid, there would be release of T3, T4, right? These T3, T4 will work to increase BMR and all the body systems, right? So many things would be done. So thus, that's the entire process, right? So over here, first was this hypothalamus to pituitary, right? That was the first. Second, we need to know in detail about what really happens in thyroid. That is why, say, we will be putting this extra stress on this. As you will know, that once you understand this thyroid process, right, how it releases T3, T4, you'll find that for every step, there would be, if anything goes wrong, it will lead to changes in it. And once it is changed, this T3, T4 level, either they are increased or decreased. We'll be talking about its level, this, that, everything, what is free T3, free T4, everything. So just hang on, right? But over here, when this T3, T4, it increases or decreases, it depends upon this, what really happens in thyroid, right? Why iodine is important, right? All those things will come. And once they are into the circulation, what will they really do to the body? That's the third part. So that's how we'll be studying it. So first is the easy hypothalamus to pituitary, this thyroxine releasing hormone, and this is thyrotropic releasing hormone, and then anterior pituitary, it is releasing thyroid stimulating hormone, and it goes to thyroid. All these things, they are happening in blood, correct? Everything is happening in blood because this is anterior pituitary. So over here we know that it would be going via this thyrotropic releasing hormone will be going via hypothalamo hypophyseal portal system, correct? And this is nothing but blood capillaries. Good, right? Then this thyroid stimulating hormone, that will also go via blood, so it will be into the blood and it will reach to thyroid. Then thyroid is doing what? It will make T3, T4. Yes, everything said, but then this T3, T4 will be poured in the blood. So again, it will be poured into the blood. This blood will take this T3, T4 to all the tissues. Once again, that is via blood. So this entire game will be into the blood, right? Okay. So starting with the very first, as we have talked about, say, this first process, hypothalamus to pituitary, we now focus on second step, right? So this is now step 2. That is what really happens in thyroid, right from the histology till the release of entire thyroid. So here it is that this thyroid, right, it will be releasing T3, T4, right? So they will be called as the thyroid hormone, right? These thyroid hormones, they are tyrosine based. So do remember, it is a tyrosine based, and they are two, right? T3, T4. But this T3, T4, which T3 is also called as the triiodothyronine, right? Because it is 3. And this T4 is thyroxine. So both of them, T3 and T4, how are they produced, right? That's how this, say, thyroid looks something like this, right? That's the thyroid gland. Okay. So if you go at a histological level, right, there would be follicles, right? And you will find that always there are follicles whenever they secrete, right? And in these follicles, there would be some cells, and we call them follicular cells, right? These are like those cells. So everyone is like that, right? Everyone is like that. So they are now called as the follicular cells. Follicular cells, right? Yeah, Honda City logo. That's right. And the way it was in pituitary, so we were telling pitucytes. So over here, we'll call them thyrocytes. You know? Thyrocytes. So cells which are for thyroid. Now we'll focus only on one of the cell, right? So see, there is a lumen over here, right? There is a lumen over here, and surrounding there are all blood vessels. True? There are all blood vessels. So let's straight away zoom to what happens in this. So this is like a full, let's make it big, right? So here is one cell. So if you really, say, go inside this cell, on one side there are blood vessel, and on other side this is that lumen, right? Obviously there are other cells like this, but our entire focus is right now on this particular gentleman, right? So he is telling that this is my apex and that's my base. So base is towards the blood vessel and apex is towards this cavity. Right? This cavity is nothing but it is like a storehouse. It is like a storehouse. It stores, right? So this is the cavity. Now the first component is coming up. These are follicular cells. Follicular cells will prepare thyroglobulin, right? It is thyroglobulin. This thyroglobulin, which is secreted by these follicular cells, right? These are follicular cells. So they are secreted by follicular cells. So from follicular cells, they will come where? They will come into this colloid. They'll come into this cavity. This cavity which is having a fluid, and this fluid is a colloid fluid. So this thyroglobulin, right, it is released. That way it would be released by every cell, right? Everyone would be contributing. So thus this thyroglobulin is now into colloid fluid, into the lumen, into the center. Right? This thyroglobulin is nothing but it is like our raw material, right? It is like our raw material, and it will be playing a major role, right? It will be helping us a lot. In fact, entire game would be running around him only. Okay, so thyroglobulin is now what is in with us. And now I'm say a schematic diagram. This, and to explain this, say I increase the size of those pins initially. So this one is like colloid, and this one is blood, right? Simple as that. So this is blood and this is colloid. And this is in between is our one cell, one of our follicular cell, just one cell. So that's how the cell is. And now the action starts. First thing, say this is a wall, right? And there is blood. So it will say that I need iodine, right? I need iodine. Follicular cell would say iodine is needed because we are thyroid and we need to have iodine. They say iodine can't come by himself. So no problems. They'll say deploy sodium. So it is now sodium, iodine, sorry, symporter. Symporter means both of them will come together. So symporter. So two sodiums they enter, but at the same iodine, one iodine also comes. So now iodine is into the follicular cells, right? Now in that, this iodine is now our prime focus. So I am just highlighting it, right? This iodine. So that was because of this sodium iodine symporter. What was sodium iodine symporter? It was nothing but it was this channel, right? Which was behaving in this way for sodium and iodine together. Similarly, there is one more channel. Now this channel will open where? It will open into that colloid. So it will say, okay, iodine, you go here. So now iodine has reached into the colloid solution. But because the ions are to be balanced, so chlorine in same quantity will go inside. So they are balanced. This is what is called as the pendrine, right? This one is pendrine. So till this point, this was step 1 and this was step 2. Highlighting these steps, step 1 and the step 2. So once that sodium and the iodine, it came from blood, and from blood, iodine, it entered into that colloid. Fair enough? Okay. Now the game would occur into the stadiums of colloid, right? So in colloid, and I am doing like this. So we know that we are now into the colloid, right? We are into the colloid. So in colloid, there is thyroperoxidase, right? in it acts on iodine because that's the only thing available, and it would be converted to stable iodine. This process is called as oxidation. Oxidation. And obviously it is the oxidase only who will be doing this process. So thyroperoxidase does only one thing. This Bhatakti Atma type of iodine, he is given a stable iodine. Right? Now this stable iodine, this process is called as the iodination. Iodination. What it will do, this was step 3, correct? And it'll say this iodine, why it should go anywhere, right? We do have that thyroglobulin, right? Remember thyroglobulin we just saw over here, and we said that this is the material, raw material, which we'll be using again and again at so many points, right? So this is thyroglobulin. This thyroglobulin will come over here. Thyroglobulin will say, yes, I am to like, say I do have so many branches, right? So iodine, why? Well, you can hang on with any of my one branch. So iodine will say, chalo, theek hai, I'll hang on. So this is the 4th step. This is nothing but thyroglobulin, right? So finally we have one nice stable branch for thyroglobulin. Pendrin is nothing but, pendrin is just a type of channel which will allow iodine on one side, and the counter is chlorine, because they both are negative, so thus the ionic balance is needed. So that is what is the pendrin is. Okay. So here it is, thyroglobulin. Now actually say anything more about pendrin or anything more about sodium iodine symporter, it's not, because most of the processes, they will be based on whether the lack of iodine, or if there is any change in, say, thyroperoxidase is not available, or if the oxidation is not happening. Those are the more important points, right? As compared to that knowing something extra about pendrin. What exactly are we looking at? Nothing, right? That was its function, period. Okay. So now this thyroglobulin, right, which is our main candidate. So I'll just write thyroglobulin like this, right? This thyroglobulin, it will say that free iodine, right? Free iodine was there, and then it became stable and it got attached to thyroglobulin. When there is one iodine is attached, right? So when there is one iodine, it is attached. So obviously it is called as the mono, right? Iodo, and this is tyrosine base. So one mono, it is tyrosine. So we'll say MIT, right? MIT. Monoiodotyrosine. So in which there is only one iodine. Now possible, right? In some case, even 2 iodines are attached, because thyroglobulin say, okay, I got enough branches, so come join, right? Either one can join or 2 can join. If 2 join, so now there are 2, so we'll call it diiodotyrosine, same way, right? Diiodotyrosine, which is called as the DIT. So that was MIT, this is DIT. Once this is there, now we have got MIT and DIT. Then there is a glue, right? There is a glue which sticks together, and that glue is thyroperoxidase. Already we talked about it, right? Thyroperoxidase. Where we saw this? It is just here, right? Here. Thyroperoxidase. That one who converted that iodination, that is that iron, to stable iron, right? So same thyroperoxidase, once again it comes into picture. He'll say, see, my work is like glue, right? I can really work on it. So what it will do, they both would come to him, MIT and DIT. That say we do have so many MITs, we do have so many DITs, so you just join them. He'll say no problem. And the process would start. And process would start in this way. Now understand. That because of thyroperoxidase, if there is one component of MIT, right, one component of MIT and one component of DIT, if they both join, right, so it means this unit is now called as T3. So actually what it is, here is thyroglobulin. On one there is one iodine. Then there is another thyroglobulin, right, in which at two places the iodine was joined. And then when both of them they merge, this is called as T3, right? So in T3 there is one MIT and one DIT. True? So that's why total, say iodine, how many iodine? In MIT it was 1, in DIT it was 2. So 1 plus 2, 3. So that is T3. What happens? Yeah. Thyroglobulin. Thyroglobulin was the raw material, right? In the beginning we talked. That is thyroglobulin, which is released by follicular cells into the colloid solution, that is into the cavity, and it is stored over there, right? Then it keeps on working as it is needed, because it is the main hero of this entire game, right? Okay. Now this MIT, it is out. What if there are two DITs, they join together, right? When they do it, so that means there are two iodine in this and two iodine in this, so this is what is called as the T4, right? That is T4. So that's how here also, right? It is this thyroglobulin, there is another thyroglobulin, but this time there is one iodine, there is one iodine, this is one iodine, this is one iodine, and this entire thing will now be called as T4. And quantity wise, you'll get more T4, like large amount of T4 is present. All these things, they are happening where? These things are happening into that colloid, right? Into the colloid solution, into that cavity. Now, both of them, right, whether it is T3 or it is T4, right, they all join together, right? They join together because right now it is the colloidal cavity. So once again, we are drawing our original figure. This, right? And here it is the colloid, and this one is the blood. It is necessary to send this T3, T4 into the blood, then and then they will work, right? So somehow we have to send them. And this is thyroglobulin. And in this thyroglobulin, we do have T3 and T4 attached with him, right? So they are attached. We are coming to the difference between T3, T4, right? All right, that is a good suggestion, right? I'll add the title. I'll add the topic in title. Yeah, Pranav, that is okay. That is good. Okay, so thyroglobulin, right? It is now T3, T4. They are attached. Now they want to get released into the bloodstream. So we need to reach here, right? This is blood, and over here it has to enter into the cell. This is follicular cell, and this is follicular cell. Now in follicular cell, when the entry is to be made, it is called as endocytosis. When it has to exit, so it is called as exocytosis. If anything is to be thrown out, exocytosis, right? Now it has to enter, so it is called as endocytosis, entering into the cell. So it enters, right? It enters. When it enters, right, this thyroglobulin to is a lamba chauda, right, big protein, right, in which T3, T4, they all are hanging. So once it enters, there are cutters, right? There are cutters, right? They are lysosomes. So those lysosomes, they are like cutters. The moment they see this, that okay, this is thyroglobulin, right? Chalo, attack, right? And it will implement its catchy on thyroglobulin. And that scissor is proteases, right? It is an enzyme, ACE, it's an enzyme. This enzyme will act on thyroglobulin and tuck, right? It will start cutting. So what really happens in this case? This T3, T4, now they are released. Now, when they are released, there is one more channel. See, so many different channels are there. This channel is specific. It said this is a royal entry only for T3 and T4. I will not allow anyone else. T3, T4 will say, okay, here is my ID and out. T4, my ID and out. Name of this is MCT. What MCT is? Monocarbonate transporter, right? It is a transporter. So transporter is, it will just allow T3, T4 to go out. Now they are into the blood, right? After so much of effort, T3 and T4, they both have managed to reach onto the blood, right? Okay. Now, when we talk about the comparison between T3, there is one very important thing. T3 and T4. T3 is rapid fire, right? It is active. It acts fast. It is active, right? But it's, if you talk about its half-life, right, that is short. So just 1 to 2 days. Within 1 to 2 days, its effect becomes half. T4, it is definitely less active, but it acts for long, right? So that's why when we talk about its half-life, it is 6 to 8 days. This was 1 to 2 days. This is 6 to 8 days, right? So it acts long, right? But its effect is less, right? So over here, the most difficult part, right? Difficult part is over. But from this point onwards, the things are absolutely easy, right? So you can expect definitely few questions from this part. Okay. All right. Now, when we talked about hypothalamus, to it goes to anti-pituitary, right? There is thyrotropin releasing hormone via that portal system, and then the thyrotrophs, they release the TSH, and it will go into blood. You know this part, right? So I'm not writing it, or should I? Should I? Just for the reference. Okay, let's write in very brief, right? So this is hypothalamus, right? It leads to release, goes to this anterior pituitary. Anterior pituitary is A is for adeno, so it will release, and it will release that secretion, and it releases this TSH. TSH over here, it is the TRH, right? Thyrotropin releasing hormone, and that travels via HH portal system. You know what is HH, right? Hypothalamo hypophyseal. Hypophysis means it is another name of pituitary, and this is TSH, it is released, and they are, that is by thyrotrophs, and these thyrotrophs, they are basophilic. So they are basophilic, and this basophilic will give that blue color, B for B, blue color. And this TSH is now released into blood, correct? And from blood, it will be going where? From blood, this blood, it will lead to the point where once again we are drawing this, right? And this is our colloid, and this one is blood. So yes, it reaches to this blood, right? It reaches to this blood, right? It has arrived. This thyroid stimulating hormone. Now this thyroid stimulating hormone, it can't enter into follicular cell directly. So there is a receptor, right? This is which receptor? It is TSH receptor, right? So here it is a 7-pass receptor. So 1, 2, 3, 4, 5, 6, and 7. And then over here it acts. So when thyroid stimulating hormone, right, it comes to thyroid stimulating hormone receptor, it comes over here. And then it sends the signal inside, right? 7-pass, and it sends the signal. Okay, come on, right? We need to do something. This is so powerful. It will say, okay, don't worry, we'll go for activation of all the processes, right? It releases the intracellular protein, and this protein will act on everything. First was that iodide, right? Iodide pumping, that iodine was coming and then it was pushed, right? Then second was thyroglobulin synthesis, our raw matter production. Then the third was that when this iodine converts to stable and it connects to that thyroglobulin, so it is the iodination, right? Iodination, the process of iodination. And finally, when this entire loaded thyroglobulin, he enters into by endocytosis, and then over here lysosome acts on it with that protease scissor. It cuts this entire big thyroglobulin. T3, T4, now they are released and they go out into the blood via that MCT, right? Monocarbonate transporter. This intracellular protein which are released because of this thyroid stimulating hormone helps in that also. T3, T4 in blood. So that's how that actually the moment this TSH comes, right, it gets attached to this receptor, it sends the strong signals inside, and this entire process, it is done, right? It is happily done. When it is done, now this T3, T4, they will come into the blood, right? So this is now the new location of T3, T4. So T3, T4, they are now in blood, right? So we'll now, they are into blood. Okay. From this point, in blood there are plasma protein. Now see what happens after so much of efforts, right? See the motivational part. At times we say, Arey, I worked so much, right? But still I got 70%, right? Or I got 60%. You will get lots and lots of motivation from these T3 and T4, right? They worked so hard. But then there comes the villains, right? These plasma protein. There is thyroxine, and this is major, right? Thyroxine binding globulin, right? This globulin, it is a protein. It immediately starts catching those T3 and T4s, right? Then there are albumin. They also help. Yeah, chalo, I'll also help you, right? And in the process, over 99%, right? Almost over 99% of which are at T3 and T4, they are captured, right? These proteins, they bind to them. And when they bind, right, see, they bind, and once they are bind, they are actually inactive. They are useless. They are inactive, right? Biologically, they are inactive. So they won't be taking any part in that. So when in the lab we'll see T3 T4 levels, right? So T3 T4 levels, they are these levels, that how much T3 and T4 they are floating into the blood, but how much is active? Well, that active is hardly even less than a percent, right? It is that less, and it is that less T3 T4 is handling so much in the body. It is increasing the temperature, it is taking care of the moods, it is taking care of the so many metabolically active, and plus basal metabolic rate, right? Everything. It is that less than 1%. So what would happen in case if this binding thing goes away? So in that case, there would be loads and loads of this T3, T4 into the system. And then you can think that what chaos it can create. That's what we'll see in the pathology part, right? So that's what I said, that these processes, they are so important. And then if anything goes wrong to one process, it will lead to that big side effects, right? Okay, so this is what is bound. How much is unbound? It is whatever that less than 1% which is unbound, that is active. And when we'll see the lab values, right, I'll give you both the lab values. That is the total T3, total T4, and the free T3 and free T4. So it is the free T3 and free T4, they are active, right? So in other words, free T3, T4, they are active, and we are interested in that because they will be leading to all those cellular action, right? So they reach to these cells. They reach to these cells, and these, once they are into those cells, and they will start working. But meantime, they'll say, yeah, this T4 is very slow, right? So if we really want to work, so then we need to convert that from T4 to T3, right? So he'll say, okay, again, there has to be an enzyme. So it is 5-deiodinase. Iodinase. How to remember this name? Deiodinase is, so it makes sense, right? It is an enzyme. In T4, do you remember there were 4 iodines? And over here there would be 3 iodines. So he is devoid of 1 iodine. Devoid means taken away. So that's why it is D, right? So it is deiodinase. So T4 is now converted to T3, right? This T3 is now going for that thyroid hormone receptors, right? Because say this T3 is okay, but now unless and until they are acting on something, so they need receptors. So that is where there is a thyroid hormone receptor. Now this receptor is what will go for, it will take all the way for gene expression, right? Gene expression. So that is where all that synthesis will occur, and it will control that. So this is what is called as the regulation of gene synthesis. Now, what if this hormone is not reached? What happens in its absence? Say in absence, right? In absence of this T3. So this is, let's say, the entire gene, and let's say this is one area which is called as the response unit or the response element, where it is necessary to create any of the response. So this is like response element. Under normal circumstances, this particular area, right, this particular area, it is covered, so that no one can come and act on it. So this is like there is what is called as the core pressor, right? It presses the core that no one should act on it. So normally, this is N is normally, right? I'll just write normally. And it is called as the core pressor. Core pressor. But now the T3 enters, right? So let's change the color. T3 enters. T3 tells that let this core pressure go out of here, right? Because of this core pressure, it is not allowing any of the gene expression to occur, right? So it is not allowing any of the internal process to occur. So he'll T3 would say that I do have one of my khabri, right? And he is someone who will take me all the way to that response unit, and he'll say, okay, this is the T3, right? They both join hands, and this one is co-activator, right? Easy name, co-activator. So both of them, T3 would say, okay, bro, let me take me to this response element, and let's work over there. And it goes to that point. He takes him, and that leads to all those gene expression. Everything whatsoever is happening into that cell would now be under the influence of that T3, right? So that's how both of them, they will be working. Now this T3, after so much of efforts, what it is going to do? This T3, say whenever you need heat production, right? Heat production. So it will break down glucose, break down fats, right? So breakdown of fat, glucose, right? So that energy is produced. So it will produce energy, right? It is known, right? T3, T4, that whenever there is sympathetic system, right, it will stimulate sympathetic system. So when there is in this sympathetic system, so there would be increase in the cardiac output, correct? Cardiac output. There is increased heart rate. There is increased respiratory rate, because everything whatsoever needed for fight and flight response. So whether you want to run away from that situation or you want to fight it out, but sympathetic has been active, so there would be increased cardiac output, increased respiratory rate, there would be increased perspiration, right? Increased sweating, right? All those things would, which are the sympathetic, right? That would happen. Meantime, T3 would also act on, say, with association of growth hormone. So it will say, okay, growth hormone, you are there. He'll say, yes. So chalo, both together take care of those long bone developments. So long bone development. That is what happens when it works. T3 plays a major role even in the brain development, right? It plays a major role in that. So thus collectively it would increase basal metabolic rate. That is what it will do. Basal metabolic rate, thus acting on all the cells, right? And that's how it increases. Now, this is a very delicate process, very intricate. You must have known that those who are taking that T3, those tablets, right? In whether hyperthyroidism or hypothyroidism, but they have to take those tablets very regularly. It's like whenever there is high T3 or T4, right? It would immediately tell the hypothalamus that this is very high. Hypothalamus will say, okay, really? Let me talk to anterior pituitary, right? It will say anterior pituitary. It will say, stop. TRH, I am not sending. He'll say you are not sending TRH, so then what should I do, right? It'll say, okay, forget, I am also not sending TSH, thyroid stimulating hormone. When it is not said, yes, this high T3, T4, right, it would drop. T3, T4, it would drop, right? And this is what is called as the negative feedback mechanism, right? And then vice versa. If this thing goes low, if this thing goes low, hypothalamus would say, okay, no, right? Thyroid releasing hormone is released. It will say thyroid stimulating hormone is released. There is increase in T3, T4, and things are good, right? So that's how they keep on working. Now, as said, that we shall talk about some normal values, right? Some normal values. These normal values, no. This is PCT and proximal convoluted tubule and collecting duct, right? So just correct in that also. Yeah, yeah, that's right. So just remember this, right? I'll correct in that also. Okay, so normal levels in T3 and T4, right? They are pretty high. These are what's called as the total. So total values, right? It is like 100 to 200 nanogram per deciliter or the 100 ml of blood. T4, even that is also 5 to 12 microgram. Yes. So T4, that is 5 to 12 microgram again for that deciliter. Then this TSH, thyroid stimulating hormone, right? That is also 0.4 to 4, right? There is a bit wide range, but this is ml per liter. These are the total values, but these total values, they are of no use, right? Actually, we need to see how much is effectively. So that is where you go for free T3. Now this free T3, we said that it is almost less than a percent. Yeah, actually 100 to 200 nanogram per DL deciliter is 100 to 200, against that free is just 0.2 to 0.5 nanogram per deciliter. So less, right? Same thing happens in case of even T4. It is just 0 point. This is like free T4, right? 0.8 to just 1.8 nanogram per deciliter. So these are the free. Actually, we are more interested in that, right? You know the reason, because the rest of the T3, T4, they are bound. Once they are bound, so then they will not at all be active and they won't be working, right? So when there is increased T3, T4, I already answered that. I already answered, right? This question has come for the third time. It is PCT and CD, right? Proximal convoluted tubule and collecting duct, right? So that distal convoluted tubule, please correct it, right? In that also, I'll correct it in that PDF, right? But just, and I'll put it into the notes also, and I'll put it into the comments also, so that in future you'll automatically be able to remember it, right? I'll correct that. Okay, coming back to this, increased T3, T4, right? So that is what? That is hyperthyroidism, right? It is called as the hyperthyroidism. Now, as you know that this T3, T4 is increasing the BMR, right? That was a normal, but over here it is increasing beyond range. So obviously that will lead to anxiety, right? everything, they become hyper. So there is hyperactivity. They just can't sit at one point, right? There is irritation. That is what would happen, right? And because it is acting on muscles, it will lead to those tremors. It will act and on those sweat glands, so there would be heavy sweating, so much so that it has got effect on even gonadotropins. So there would be, say, even skipped periods. That is what is seen in case of hyperthyroidism. Now against that, the complete ulta is hypothyroidism, right? So in hypothyroidism, there is decreased T3, T4. So first is there would be weight loss, right? BMR and everything is totally disturbed, right? There would be, in fact, the muscle loss, there would be lethargy, person would be very fatigued, right? And not only the muscular, even the smooth muscles, they are also affected. So there'll be improper peristalsis, so which will lead to, say, constipation. Then as those sweat glands, they are not working, so skin will become dry. So dry skin, right? All these things, they will lead to, say, what is called as the hypothyroidism, right? Why T3 causes skinny? Okay. So that was for today, right? Okay, we have overshoot the time a bit, but say this is what really happens in case of this. So today we talked about ADH, we talked about that oxytocin and prolactin, and finally the thyroid hormone, right? Tomorrow we'll be dealing with the pancreas, right? Insulin, glucagon, somatostatin, and then let's see how the time permits, and accordingly we'll be taking some more topic, right? So thank you so much and wish you all the best, right? Study well, and tomorrow we meet at the same time. Thank you. And I'm saving this file, and within few minutes I'll be putting it into our shared folder, right? Thank you.